Right, Matrix, in this lesson we're now going to go to 3 dimensions. Okay, now I wanted to show you what a 3-dimensional object looks like. I want you to visualize this CD as a pole that's running perpendicular at right angles to the ground. The ground, ABD, is called the horizontal plane. It's flat. Then you've got two vertical planes going up. They're standing up. Okay, and then you've got a slanted plane or an inclined plane. But let's look at these before we look at inclined or anything like that. I want you to focus on triangle ACD. Have a look at that. That's a vertical plane. Now, if you look at it, it's kind of standing up. So if we go down and have a look at a vertical plane ACD, you'll notice that this is angle theta. That is a right angle there. You can't really see it in the top picture, but this is a right angle there, and this is what we call a vertical plane. Okay, it's standing up. Okay, there we go. Have a look at that vertical. It looks as if this is not 90 degrees, but it actually is. That's the angle there. The other vertical plane, if you have a look at it, is BCD, this triangle there. Okay, now careful. Watch out for this angle beta here. There's a big difference. This is angle phi. We call that phi. Look at this here. Again, 90 degrees. This is vertical. It's a triangle that's actually standing up. Okay. Then you've got the shaded triangle is the flat triangle on the ground. And let's have a look at what that looks like. There's the flat. There's the alpha. It's flat. This is that shaded triangle. We call this the horizontal plane. Okay. Careful with that. Then the other plane that you get is going to be, I want you to look at triangle ABC. Triangle ABC is inclined. Now be careful. That angle there is beta. I'm going to show you what it looks like. It goes something like this. Have a look here. The inclined plane. There is angle beta. Can you see that? That's inclined. It's slanted. It's sort of slanting down. Okay, but now you can't say that this angle here is alpha plus theta, because that's flat, and this theta here is going to a triangle that's standing up, is vertical. That's horizontal. That's flat. That's vertical. Remember, that is vertical, and that would be horizontal. So this triangle here, ACD, would be, if you look at it from there, it would be from this side. Okay, it would be up, and that other triangle is flat. That's where the shaded triangle lies. Okay, good. So it's important that you see this. We're going to explore this with an example now. So let's go to an example quickly involving 3-dimensional trig. In this diagram, what we've got here is the ground. ABC is a triangle on the ground, but what we've got here is we've got a vertical tower. Now I'm going to draw this in purple here. There's a little tower. Now it could be an antenna, anything like that. Going up, or a pole going up, a flagpole or something. It's a tower that's going up, and it's running at right angles to the ground. Then we've got maybe a little string or a piece of rope that's attached to the top of the tower, and it goes all the way down here, and then another piece of rope that goes down there. And we want to join A and B. So the distance between A and B is going to be 1,500 meters. Now notice this angle here. This is important. This angle here is going up. Okay, it's 25 degrees. This is the angle on the ground. It's 30 degrees. This theta is going from the ground up. Okay, these two triangles here are vertical. Okay, they're running at 90 degrees. Okay, 158 is the length of the tower. Okay, and so this gray triangle is on the ground. Okay, so what I want to do is I want to show you something now. If you have a look at the triangle, say for example you look at triangle ADC. Let's just draw this quickly. If I look at that vertical triangle there, just have a look at this. Okay, there's a 90-degree triangle. The top of the tower is D, and the bottom is C. So the tower is 158 meters. Okay, this is the length of AC, which is really this. That's the length of AC there. Can you see it there? That's AC. That's the length of AC. Okay, then we've got AD, and the angle there is 25 degrees going up. Okay, now the first thing I want you to do is I want to calculate. So what I'm going to do, there's two parts to this example. We want to calculate the length of AC. What is the length of AC? Then what I want you to do is I want you to calculate the length of BC. What would be BC? And then C, I want you to calculate what is angle theta. Okay, now let's have a look. If you look at triangle ACD, here it is. It's a right angle triangle, and we want to get the length of AC. Okay, before I even do that, what I want to do is I want to get that missing angle there. Now come on, what is this missing angle here? If you look at this is 90, that's 25. So what would be angle D? What would that angle D there be? Well, if you think of it, they all add up to 180. So this missing angle would have to be 180 less the 90 degrees less the 25. Work that out and you get yourself 65. So this angle here is 65 degrees. So let's put it into there, 65 degrees. Can you see that vertical triangle? When you look at it from this perspective, it looks weird because it doesn't look like a right angle triangle, but because it's in 3D, you've got a vertical tower and a horizontal plane. It looks like that, but if you actually take it out and look at it in its own right, it's a right angle triangle. Now there's two ways you could find the length of AC here. The one is, we're going to go back to grade 10. Do you remember how this worked? If you look at AC, okay, what we could do is there's a connection between AC 158 and 25 degrees. Okay, you could do that. You could use your grade 10 trig, and how it would work is something like this. Okay, if we look at that triangle, we could say, well, if you relate 25 to the two sides, this would be opposite. That would be, the AC would be the adjacent side. Okay, now opposite of adjacent, if you remember, was tan. Oh heaven, another hour of algebra is tan. So tan 25 is opposite over adjacent. So this is how we can write it. We can say the tan, okay, the tan of 25 degrees is the opposite, which is going to be 158 there, over AC, which is unknown. So it's opposite over the adjacent side, which is AC, and we don't have AC. We want to find it. Now if you multiply both sides by AC, well, AC comes to the top here. There we go. Okay, 158 meters there. Now divide both sides by tan 25, and what would you have? Let's have a look at that. Okay, so let's have a look. What would the length of AC then be? It would be 338,83 meters. Just check that in your calculator quickly, 338,83. That's the one way we could do it if we used grade 10. But there is another way that you could do this quite easily, and that would be the sine rule, because look, you've got a whole lot of angles and a side. So how could we do that? Well, if you think about it, we've got this little triangle here. Let's just redraw it quickly there. Okay, there you've got the 90 degrees. This is angle, okay, that's angle ACD. This is 158 meters. You've got, this is going to be 25. That is 65 there. And you want the length of AC. Now, using the sine rule, we can say AC divided by the sine of the opposite angle. Okay, so it's AC over sine of the opposite angle is equal to, the other known side is 158 divided by the sine of 25 degrees, using the sine rule. So you can, in right angle triangles, you could use the sine rule, or you can use just your normal trig ratios from earlier years. So let's do some cross multiplying. Let's multiply both sides by sine 65, and of course it would cancel here. Okay, there's sine 65 and sine 65, and those cancel there, and you're left with 158 multiplied by sine 65, all divided by sine 25 there. Now work this out in a calculator, and guess what? You get exactly the same. Okay, so there's the length of AC. Good, and we can then write that into the triangle there. So we can go and say, well, AC is 338 83 meters. There we go. Alright, now, that's great. Now, what about the next question, which says calculate the length of BC? Okay, now, if I look at the top triangle, I haven't got any angles that are given to me except the 90. So you could say BC over sine this angle, but that's not going to help us at all. But maybe we can use the flat triangle here, because look at this. You've got, in the bottom triangle, the gray one, two sides and the included angle. Two sides, those two sides included angle. So we can use, what rule is that? The cos rule. So if you draw that triangle, let me just show you quickly here. If you actually go and draw triangle ABC, it looks like this. It's the gray triangle on the ground. That's C, B, and A. This angle here was 30 degrees on the ground there. Just do that properly. 30 degrees there. And you've already worked out this side is 338,83 meters. This one is 1,500 meters. And guess what? BC is easily obtainable by the cos rule. So what do? We say BC squared is equal to, okay, the 338,83 all squared plus the 1,500 all squared. Okay, now let me move that across a little bit there. Subtract. Okay, now I'm going to go over here. 2 multiplied by the two sides. Okay, you multiply by the two sides and then multiply by 2, and the cos of the included angle there, 30 degrees. Now, if you then work that out in a calculator, just check with me. What would BC be equal to? Well, let's work out BC squared. That, if you work out that squared plus that squared minus 2 times this times the cos of 30, just check if you get the same as me quickly. 1,484,499,606. Okay, and then square root it and round off to say 1 decimal place. In this case, we'll go to 1 decimal just for fun. 1218,4 meters. Have a look at that. That's BC. Just check it. The cos rule there. Okay, so that gives us BC. So watch out for that two sides included angle. You use the cos rule. Okay, I'm going to write it onto the triangle here. This is going to be 1218,4 meters. Okay. Alright, now the next is how do we get the angle theta? Well, now that I'm going to use grade 10 stuff. If you look at this, we've got theta is opposite over adjacent. That's the opposite over the adjacent in that right angle triangle. Let's draw that triangle and see what it looks like. Here we go. Okay, that triangle looks like this. That's that vertical triangle. Remember, it's a 90 degrees. That's going to be C, D, and B. That's your theta. You've already worked this out. And you've got this as 158 meters there. So, what is this? This is opposite, and that's adjacent. So, what do we know? The tan of theta is the opposite over the adjacent. See that there? Now, all you've got to do is, I would go shift tan of this fraction, go like that, shift tan of the fraction, round off to 2 decimals, let's say, and you're going to get 7,39 degrees or 7,4, anything like that.